Okay, good morning, everybody. So we start our morning program. Just a small update for tomorrow. The good news is that there is no update, actually. So Nima is supposed to arrive in the morning, and we indeed will have then the evening lectures by him. But today we start basically the new round of lectures. And the first one will be by Jacob Bourjaily, talking about the vernacular of the S matrix.
Let's see, this is working great. Thank you so much for the invitation to be here. The story I'm going to tell over the next 3 lectures is related to the role of geometry in our understanding of the S matrix. And in recent years, the geometry has appeared in many places, including in loop integrals and loop integrands and periods. But that's not the point of this talk. It's really about the building blocks or the basic vocabulary, the vernacular of the S matrix, and one of the particular places in which geometry makes an appearance and what we understand about it. It's part of a fairly well-developed story that it's my pleasure to review for you here. This lecture will be mostly setting the stage and laying the groundwork and giving you some intuition about the basic building blocks and what these objects are. They're called Onshell functions. And it will involve some review from Shruti's lectures and from Yaroslav's lectures that will, with a different take on it slightly. And then in the next lecture, we'll talk about the combinatorial structure of this geometry. The fact that there's a combinatorial structure is very interesting. And in the last, we'll go back to the geometry and kind of understand it from a few different angles. But to set the stage, you must know that we've made enormous advances in our understanding of scattering amplitudes. We now have efficient tools that compute perturbative loop integrands to relatively high order, especially in nice theories, and an increasingly wide variety of quantum field theories. We have things like Onshell recursion. We have unitarity-based methods, which are extremely robust, much more general for general quantum field theories. And the coefficients, when we write down an integrand basis like this, are these funny-looking pictures here, which are called Onshell diagrams. That's part of the point of today's lectures, to review those. We also have, you might know about the positoroid stratification. That's the point of this afternoon's lecture, or the amplituhedron. And in all of these stories, there's a geometry behind the scenes that plays an important role, and that's really the theme of this talk. But just to set the stage, so to kind of, start with the punchline and that we're going to slowly develop as we go, there's a very interesting geometric correspondence between classes of pictures like this, which encode products of Onshell S matrices where the internal lines are Onshell. So these are called Onshell diagrams. I'll define them more rigorously in a moment. I'll tell you what the colors mean and whatnot. But in a general quantum field, there's a beautiful correspondence between these kinds of objects, which are the vernacular with which we need to talk about the S matrix, or part of the vernacular, and 4 theories that are massless in 4 dimensions, which conveniently includes a lot of theories that we care a lot about, including virtually all of the standard model. There is a correspondence between these objects, so the product of all of the amplitudes integrated over the Onshell phase space of all the internal lines and summed over all the states being exchanged, and certain volume integrals over a Grassmannian manifold. And I suspect that might be new vocabulary for some of you, so I want to review that slightly, and we're going to, of course, see this in much greater detail. But in broad strokes, the correspondence is, for any theory, planar, non-planar, supersymmetric, non-supersymmetric, as long as it's 4-dimensional and massless, there is the following correspondence. An Onshell diagram like this, which encodes perturbative scattering amplitudes, at least integrands, and the coefficients of integrals, and this some sort of volume form, and the volume form in particular, so substrata means some subspace inside the space of the Grassmannian, which I'll define later, with some volume form that depends on the theory, but the geometry does not depend on the theory. And just knowing that this correspondence exists implies some really powerful intuition in both directions. For example, volume-preserving diffeomorphisms over here. Diffeomorphisms is an infinite dimensional group. Volume-preserving is a simple restriction on those, codimension 1, and so you'd expect that the space of this, of course, leaves the function invariant, so you expect that volume-preserving diffeomorphisms correspond to physical symmetries of these functions. And indeed, every time we've checked, we don't know what these symmetries mean. In some cases, in the case of planar n equals 4, for example, these symmetries have a name, they're called a Yangian. but they seem to exist for non-planar theories and for non-supersymmetric theories as well. What they mean and what they mean for amplitudes, unknown. And the sets of kind of coordinate, these volume-preserving diffeomorphisms can be generated by cluster mutations, which is an interesting story which I won't talk very much about in these lectures. And there's a beautiful algebraic structure there. So these things are sometimes called Onshell cluster varieties, the geometries here. And the different theories have different kinds of structure in the picture. So for example, planar theory with maximum supersymmetry, you don't need to draw any arrows, so they're undecorated planar graphs with two colorings. Simple class of objects to talk about. These things are bicolored, undirected graphs on the plane. And in this case, well, I'll show you how to construct these kinds of matrices. The volume form is just a logarithmic form, d log, d log, d log, d log. Couldn't be simpler. And the names of these subspaces are called positroids. And in fact, the entire theory is encoded by combinatorics in a way that we'll talk about in this afternoon. But if you were to, and the symmetries are called the Yangian, but if you were to remove supersymmetry and say, so to differentiate between the plus helicity and minus helicity gluons, then you'd have to draw arrows, in which case this volume form would change sometimes. In this case, the factor is 1 to the power n minus 4. But in a more general, if you drew the arrows some other way, there might be a non-1 sitting there with raised to the power n minus 4. So they're almost the same as the functions, which is very interesting. For non-planar theories, you can proceed in exactly the same way. For n equals 4, at least, non-planar, the volume forms are also d logs. And for non-planar pure Yang-Mills, they're some factor to some power. So there's the volume form cares about the theory. In a theory with more than one kind of particle, or one kind of superstate in the case of super Yang-Mills, you would have, like if you wanted to talk about massless QED, you would have to distinguish in these arrows here between the species, whether it's photons or electrons, say. Okay, but this immediately raises some interesting kind of geometrical intuition behind things. For example, functional identity, how many functions exist? Although there's an infinite number of diagrams you can draw, it's pretty easy, we'll see why. There's essentially a finite number of different functions to talk about. So this finite list of data encodes everything. All of the functions are encoded in a finite list. But how many are there? I don't know. How do we name them? How do we label them? What functional relations do they satisfy? This duality immediately implies that geometric relations on this side imply functional relations on this side. Meaning, for example, if you take a homological identity, meaning that you just carve up like you triangulate some region in different ways, that clearly corresponds to a sum of diagrams which is the same no matter how you carve it up. That's a kind of functional relation. What relations do they satisfy? Outside of the case of planar n equals 4, we don't know the answer to it, but it's easy to construct, and this is a generally true statement. What are these infinite dimensional symmetries, and do they have anything to do with amplitudes at all? That's not clear. In n equals 4, it's nice because it turns out that in general, the symmetries that preserve each diagram are not the same. But in planar n equals 4, you can answer a bigger question, which is what is the set of symmetries which preserve all diagrams? That's the Yangian. And usually, these are just little building blocks, and maybe the symmetries don't overlap right. So maybe they don't actually apply to amplitudes. Do you have like loop level recursions, for example? These are all open questions as soon as you remove maximum supersymmetry and planarity. But in the case of planar n equals 4, we know how to answer them all, and that's part of the purpose of this lecture is to lay down that groundwork for you and show you how beautiful a story it is, how beautiful and combinatorial. Okay, so with that stage set, the outline for today's lecture is to start with a little parable that will allow me to introduce some notation. It's a story that you probably have heard, and if you haven't, you must. And we will then talk about, we'll motivate this set of objects and talk about what they look like, especially in the case of 4 dimensions. Okay, so I want to start with a practical homework assignment, say, which is, open up Peskin and Schroeder or Schwartz or any of your favorite textbooks and follow the Feynman rules and compute the scattering amplitude at leading order for 2 gluons to create 4 gluons. Easy enough, right? Well, unfortunately, there's 220 Feynman diagrams. Each one of those, if you remember the Feynman rules for Yang-Mills, is quite a number of terms. It's quite a mess. And before computers, this would have been utterly impossible. It's not a homework assignment you could ever assign a student. But it's even worse than that. Thinking about the problem as with, the smartest people thinking about this problem deeply, basically viewed that it was computationally intractable in a fundamental way. So there was a paper in the in 1984 outlining the theoretical challenges that were faced by the then upcoming superconducting supercolliders, the era of these big experiments with very large scattering rates. And when you get that much data, it's very important to know these kinds of backgrounds. And one of the challenges that they pointed out, one of the theoretical challenges, was that the cross-sections for 2 to 4 processes, none of them have ever been calculated, and their complexity is such that they might not be evaluated in the foreseeable future. I mean, they thought it was actually hopeless, right? And then they asked the reader to find some estimate in some kinematic regimes, maybe. What's the challenge? It's 220 Feynman diagrams. It's many terms. You have to square it. So we're talking about millions of terms at the end of the day. Well, this could have been taken as a challenge. And indeed, 2 physicists, theorists at Fermilab, Stephen Park and Thomas Taylor, picked up the challenge and got the answer. And they used every single trick in the book. They introduced an n=2 supersymmetry to relate it to different amplitude. They used the world's most powerful supercomputers. They actually thanked it in the acknowledgments. It was called the heterotic supercomputer. Anyway, and as soon as they got the answer, they rushed it to publication. The cross-section, leading order, for 2-gluon to 4-gluon scattering is given in a form suitable for fast numerical calculations. They had their audience in mind. The experimentalists need to plot background curves, things like that. So you need to evaluate it. And so what is a form suitable for fast numerical calculations? It was an 8-page rational function. And they have defined some matrices of coefficients. These are what they look like. I know you can't read it. Here's a bunch of matrices. Here's a bunch of terms. Okay, that's the answer. That's what it looked like. I mean, this is the entire paper. They basically, at the end, they apologized for not giving any details. They said, details of the calculation will come in forthcoming article, like we always promise. But then they ended on this kind of quixotic note. Furthermore, we hope to find a simple analytic form of the answer, making our result not only an experimentalist's, but also a theorist's delight. And I've asked them both about this, and it is a little unclear what they saw, but they had some vague intuition from their experience with 2 to 2 and 2 to 3 that these expressions that you get from summing Feynman diagrams could collapse a lot if you were clever enough. And this collapse, so they thought that this 8-page formula might simplify. And indeed, within 6 months, they stumbled upon a guess which must have exceeded even their wildest dreams, and certainly was a theorist's delight. That they guessed that this 8-page formula could be reproduced by that one-term expression, given in terms of spinor variable. Yeah. No, it did not.
So they did the squared MHV separately then.
They did. Yeah. And it was planar too, so they had a color sum on the outside of it. Okay. And now this expression is not exactly the way they wrote it, because they wrote about the squared amplitude, not the amplitude, so they had Mandelstams. But this notation does predate that paper, and we've already talked about it. So let me, but before I review this notation, to appreciate the magnitude of this simplification, it's enough to point out that this, well, I mean, if you stare at this even for a few moments, it's pretty obvious how to guess what it would be for 2 to any number of particles whatsoever. And so they conjectured this one-term formula should apply to all multiplicity amplitudes. And in another one-sentence abstract paper, at PRL, that the editor thought was too short, they guessed this formula. And to appreciate the magnitude of this simplification, consider when 2 gluons create 50, that's the threshold, you have, I think, 10 to the 84 Feynman diagrams, forgetting even number of terms and forgetting about squaring it. 10 to the 84 exceeds the number of atoms in the universe, okay, just diagrams. So I think you can't know that this is right. They didn't prove it, by the way. They just checked numerically that it agreed with that 8-page formula for particular kinematics. They convinced themselves that it agreed with that formula. They didn't actually simplify it or prove they were identical. But I think that once you know that this is true, it has to be viewed as an indictment on the Feynman expansion. Something is fundamentally wrong when you're adding up 10 to the 84 terms, they all canceling out to give you something so beautiful. And part of the point of this talk and the beginning is to somehow motivate that from first principles and find a new formalism for quantum field theory for which when you ask this question, you have two gluons. By the way, the arrows here all mean helicity. So you have two minus helicity gluons, create a bunch of minus helicity gluons. That's what MHV means. That when you ask that question in quantum field theory, this is the answer you get. Okay, now this was already reviewed in the school, but I just want to kind of talk about it briefly, in part as an excuse to mention the first appearance of the Grassmannian in this talk. So as you know, the spinor helicity variables follow from this nice 2x2 representation of the four momenta, and the determinant is equal to m squared, or the Lorentz invariant norm of this for a general four vector. And you'll notice that for real momenta, this thing is a Hermitian matrix. And so we have this nice algebra of Hermitian matrices to talk about instead of four vectors, where the determinant is the Lorentz invariant interproduct. For massless particles, though, if the determinant's of 0, then we can write it as the outer product of a pair of vectors, lambda and lambda tilde. And if it's going to be Hermitian, they have to be complex conjugates of each other up to a sign. And we write that in terms of angle brackets and square brackets. You've seen some of this before. So in particular, this momentum conservation here, which was the sum of the p's equals 0, becomes, I guess I didn't even write it. The sum of the p's equals 0, with all momenta incoming, becomes that the lambda times lambda for all alpha and alpha dot indices. So all the four indices, you have this sum equals 0. The local Lorentz group acts as SL2 left and right, respectively, on the lambdas and lambda tildes. So you have a very good intuition for how the Lorentz action works. And that means that Lorentz invariants are constructed out of determinants of these matrices. Those are the SL invariant objects, like det. And that's what the angles and square brackets, as I'm sure you've seen already. If you like indices and epsilons, you can write it that way if you want. So, and the action of the little group, obviously I'm overcounting my degrees of freedom. I have 2 degrees of freedom here, 2 degrees of freedom here. If we're ignoring the complex part, it's the same counting either way. There's a constraint, or rather, what's missing here? There's an Onshell momentum has 4 minus 1 degree of freedom, so 3 degrees of freedom, and it looks like we have 4. So what's up? And what's up is that you can rescale lambda by anything and lambda tilde by its inverse, and that leaves the momentum invariant. That is a non-trivial Lorentz transformation, but preserves the momentum. That's called the little group. And it's worth reminding you now, it'll come back in a few minutes, that wave functions scale uniformly under the Lorentz little group transformations. So there's some homogeneous function that depends on the helicity of the particle involved. Okay, that'll come up later. But what I think is really interesting and worth noting here is that first of all, you look at this expression and you see that it is only really a function of the lambdas. The lambda tildes only appear through momentum conservation, which I'll say more in a moment. So what does this function look like? Well, you have the data that specify, the data encoding for n massless particles in 4 dimensions is this pair of 2 by n matrices, which you can view as n 2 vectors, which is probably the natural way of viewing it, but equally well you can view it as a pair of row vectors in n dimensions. That might sound a little silly, but it doesn't matter. At the level of the matrices, we have these consecutive minors of this 2 by n matrix appearing here, and lambda tilde almost plays no role at all. Now, because the local Lorentz transformations act by SL2, and you have the little group which allows you to rescale, the set of Lorentz, so the Lorentz invariant content of lambda, this matrix, is really the space of 2 by n matrices modulo SL2 modulo little group, which is a subgroup of the Grassmannian of 2 planes and n dimensions. Is a space of 2 by n matrices modulo GL2. You can think about it as the linear span of a pair of vectors in n dimensions. And similarly, the Grassmannian GRKN, can be thought of as k by n matrices modulo GLK, or you can view it as just the span of k row vectors. The span because of the GL, right? If you're going to mod out by the general linear transformations, you're just talking about all possible things that are accessible by the span of these things, of these vectors. One reason for introducing this geometrical aside is that it does have one interesting implication, which is the intuition for what this momentum conservation looks like. So this can be interpreted geometrically as the statement that lambda is in the orthogonal complement of lambda tilde. So every k-plane in n dimensions, you have k vectors in n dimensions, and you look at the span, there's an obvious dual, which is the subspace not spanned by k vectors in n dimensions. The complementary space is the dual, and it's a plane, it's an element of GR n minus k, comma n. So it's the complement of those things. That's what I mean by perp. And so for every 2 plane in n dimensions, there's an n minus 2 plane in n dimensions called lambda tilde perp and lambda perp. And this statement here that they dot into 0 is a statement that lambda is inside the orthogonal complement of lambda tilde and vice versa. So what you can think of geometrically is in n dimensions, you have these pair of vectors, lambda 1 upper index, lambda 2 upper index, and they describe some plane, and that's the Lorentz invariant data here. And there's a complementary n minus 2 dimensional space, which is lambda tilde perp, and inside that space is the 2-plane lambda tilde, and vice versa. And this picture is drawn in 3 dimensions, which is an interesting case where this is a pretty non-trivial constraint we'll come back to in a few moments. Okay. That's a review of spinor helicity with the geometric twist on it. Okay, so this, just staring at this formula raises a couple, perhaps, kind of whimsical questions that would take quite a long time from the Park-Taylor discovery to having answers to them. The first one is there any reformulation of quantum field theory? Is there anything that we can do that, a formalism in which when we ask the question, what is this amplitude, we get this answer out? That doesn't involve summing millions of Feynman diagrams. Is there? And we will discover that BCFW, which you've learned about in the school, is exactly that formalism. Another question that's pretty natural, is there a way to generalize the Park-Taylor formula? Now, so here, this MHV character is encoded by the fact that I really only have 1 gluon of some helicity, and it's 2 to n minus 2. That's the process. To generalize this beyond Park-Taylor, the MHV case, we would have we'd generalize the number of incoming particles, which is pretty irrelevant to a collider physicist, but you can always use crossing to bring them back out to the other side. So we can talk about the non-MHV amplitudes as having more than 2 incoming particles. Okay? So we only have 1 species here, 1 helicity in the game. Okay, so now you have, k particles coming in and n minus k coming out. Is there a formula like this for that? And just by staring at it in pattern recognition, you can kind of see that this thing has to generalize to some k by k determinant. Lambda probably, lambdas, these are determinants of lambda, so whatever this matrix is, it's probably got to get upgraded to a k by n matrix. So you have some kind of k by n matrix C. And is there a formula like that? And we'll see this afternoon that yes, there is a formula like that, and there's a strict sense in which this is true. And that's one road, and in fact is historically the first road to the Grassmannian. Okay. So to even start answering this question, is there a way to make this simplicity manifest? It's worthwhile to actually go back to the ground floor and ask, what is the data on which an amplitude that we calculate? When we calculate an amplitude, what is it a function of? So an amplitude will be represented by some blob like this with a bunch of particles coming in. I take them incoming, it makes no difference. And it's just a function of the observable data describing these n states, right? Which are physical states, so they are Onshell. You have a bunch of momenta. You can talk about this this discussion's in 4 dimensions. You have a mass, and they are Onshell because you see them, and so you have this Onshell condition. So all these momenta are constrained. They also satisfy momentum conservation, obviously, but you have the momenta and the masses, and they're related to this. For massless particles, so for in general, you also have to talk about the spin of the particle, and you can talk about its helicity, the projection onto its momentum, and it will take 2 times s plus 1 possible values. But for a massless particle, something magical happens. As you all know, it becomes plus or minus the spin, so it becomes a little 2-dimensional thing. So there's a binary digit to talk about for every massless particle. And then you have a lot of other things, like which of the 8 gluons in the standard model are we talking about? There's a lot of gluons with spin 1 massless particles, but they're labeled 1 through 8, if you'd like. Or you can call them other things if you want, but there are 8 of them. And if QCD weren't confining, you could definitely distinguish them and identify them and talk about scattering gluon 1 with itself or something like that. Okay, now this is not the way we talk about quantum field theories. This is the data. We have some non-kinematic quantum numbers like colors or species, and we have some spin and we have momenta. This is not the way we talk about quantum fields, and in particular because fields need to be represented in Lagrangian and have Lorentz indices, and that generates redundancies. And this is very well known to everybody here, but it forces you to, the local description of quantum field theory in terms of Lagrangian forces you to include more degrees of freedom to describe a massless photon than it should. And this is related to gauge redundancy. And if this is usually the language that we talk about Feynman rules in terms of polarizations and things like that, which, and then we have ward identities and things like that. And people describe this as a symmetry sometimes, and it always bothers me when I hear that, because gauge symmetry is not asymmetry, it is a redundancy in the description. There are degrees of freedom that your Lagrangian cares about and that your calculation cares about that no experimentalist in the world could ever see. And then you check the ward identity to see that your answer doesn't depend on that stupid choice. Those are redundancies. That's theoretical baggage that should not be there in our calculation. So is there a way to get rid of this theoretical baggage? To not talk about the quantum fields, but just talk about the particles intrinsically. And I think that with hindsight, it's exactly this kind of unphysical baggage that we talk about virtual particles, which of course aren't seen, and we talk about gauge redundant fields, which of course are not seen. But this is the source of the obfuscation in the Feynman expansion. So if we're going to abandon the Feynman rules and the kind of, the basic toolbox that we learn, what can we say? What are we allowed to talk about at all? And that's, I think, what I want to get into now, to motivate this class of things that I'm going to call an Onshell function. So this is the class of objects that you're allowed to talk about that are not loop integrals, but that are, say, rational functions that are built out of, or that are functions exclusively of physical data, observable things that experimentalists could care about. And what kinds of things are these? Well, one example is obviously the S matrix. The S matrix we're allowed to talk about. So if we have any S matrices, we know what we're talking about. But for any local unitary quantum field theory, if you know any S matrices, you immediately have an infinite variety of further functions which are meaningful and well-defined on first principles. For example, if you had two S matrices, you could glue them together into an Onshell, what I'm going to call an Onshell diagram like this. Now, what is the meaning of this? Historically, or you might motivate it as, say, take Feynman diagrams and compute a residue on the pole of this propagator, and then that's what this diagram is. And I don't like that definition in part because it defines this thing in terms of something unphysical. This thing has an intrinsic definition, irrespective of the Feynman expansion, which is namely dictated by unitarity and locality. So because this internal state is on shell, it can travel an arbitrary distance in space and time. It's an observable state even though you're not observing it. And that means that this process over here and this process over here can be separated arbitrarily distantly in space-time. And that means that locality tells us that if in a local quantum field theory, these things have to be independent. And so whatever the meaning of this picture is, we multiply them together. And then unitarity dictates that whenever we have an unseen particle, we have to introduce a complete set of states. And a complete set of states, in particular, means summing over the quantum numbers, but it also means integrating over the on-shell phase space for the internal particles. So a picture like this is just the product of the let's say, trees here, so that we're talking about rational functions, integrating over the on-shell phase space, which is in D-1, over all of the, and summing over all their other quantum labels that we can have, helicities, masses, all the things that could be exchanged. That is the intrinsic definition of these kinds of objects. Now, so on-shell functions more generally are any graph built out of tree amplitudes like this. So imagine any conceivable network, any graph where every vertex represents a tree amplitude. And if you follow that definition, it's the product of all the amplitudes integrated over the on-shell phase space of every internal particle and summed over all the states. This is the intrinsic first principles definition of an on-shell function. And whether you're secretly computing those on-shell functions in terms of, or the vertices in terms of Feynman diagrams or not, I don't care. The point is that they're physical data that you know on first principles is physically meaningful. One thing that's worth counting when you look at a diagram like this is just counting the number of, say, delta functions in here. So every tree amplitude conserves momentum at the vertex. And so the number of delta functions, and I'm going to do this in d dimensions because this definition has nothing to do with 4 dimensions. So you have d delta functions per vertex, okay? And at every single, and then we have a d minus 1 phase space integral for every internal line. But there is always an overall delta function which is kind of stupid, which is overall momentum conservation. Any graph of momentum conserving vertices will conserve momentum across the graph. So you can always factor that part out, and so we talk about n hat d, which is this expression minus d. And that is the net number of delta functions you have in this expression. And when you compute this, you find that it is 1, and that makes sense, right? This is not a tree amplitude or anything. It is a factorization channel. So it's a number of excess delta functions in this definition. Or you can view it as minus the number of remaining integrals to do, if it's negative. And in general, when it's equal to 0, we get an ordinary rational function or algebraic function. Because all of the delta functions here, the vertices, are completely soaked up by all these integrals here. We'll see examples of that in a second. And so things with too many delta functions are kinematical constraints, or they're the boundaries of amplitudes in certain kinematic channels. And when you have negative, when n hat delta is negative, you have some integrals to do. And you should be bothered, and it's an important thing to be bothered by, which is what is the contour of integration? This expression tells you to do an integral over Onshell phase space. And once you've soaked up all the delta functions, what contour are you supposed to do? And that's an open question. I'm not going to tell you what contour to do. Maybe the meaning of this function might depend on your last choice of contour. Okay. So, I hope also some of you are wondering, this is all a great, wonderful story, but I haven't told you any amplitudes yet. We don't know any amplitudes. So, one thing that's important is that this story is well defined in any quantum field theory, any number of dimensions, whatever. You can talk about this on-shell data, and it's been known since the origins of generalized unitarity that if you understood this data, that you could reconstruct perturbation theory to all orders. And this may or may not sound surprising to you. I hope it does sound surprising to you because I'm talking about tree-level things. So tree-level data glued together in these kinds of networks of things, these on-shell functions, fully allow you to reproduce the perturbative S matrix in any quantum field theory. That's a powerful statement. But you still might wonder, we don't know any S matrix, we don't know any amplitude, so how do we start even talking about this vocabulary of objects unless I'm secretly summing Feynman diagrams at every vertex? And the answer is that something magical happens in 4-dimensional theories of massless particles. That is where all the magic is. And it goes back to that momentum conservation that we talked about, the geometry of the momentum conservation. So imagine scattering 3 massless particles. They have other quantum labels attached to them too, maybe species or whatever, but if they're massless and they have 3 different helicities, we can write down, the S matrix is going to depend on P1, P2, P3, which is the 3 sets of lambdas and lambda tildes. And we have this momentum conserving delta function. We talked about the geometric meaning of that. But I hope you realize that there's already kind of a problem for 3 dimensions, because the 2-plane, a lambda, its orthogonal complement is a 1 vector in 3 dimensions. And that means that there isn't an orthogonal 2-plane in 3 dimensions. So that means that in order to solve momentum conservation, which is that lambda perp, which is this 1 plane in 3 dimensions, and lambda tilde perp, which is a 1 plane in 3 dimensions. I'll leave it as an exercise to show that this list of determinants dotted into this 2-by-n matrix is equal to 0. But momentum conservation tells us that lambda tilde has to live here, or lambda has to live here, and lambda has to live there. Okay, either has to be both. But this tells you that either lambda tilde is actually singular. It's not a rank 2 matrix. It's rank 1, or lambda is rank 1. So in 3 dimensions, the momentum conservation at 3 particles bifurcates into 2 distinct cases. Either this function is exclusively a function of lambdas, or it's exclusively a function of lambda tildes. It's worth pointing out, well, I'll come back to that in a moment. And you can see here that in this case, lambda tilde is actually fixed by the lambdas and vice versa. So it's just entirely a function of these things. Okay, now remember how wave functions scale with the little group? that scaling, because there's no Lorentz invariant or little group neutral combination of these brackets, whatever this function is, it is uniquely fixed by little group scaling. And that's the answer in both cases. So you have, this thing is either uniquely this or uniquely that, and it can't run, it can't do anything. This is a constant in any massless four-dimensional theory. Okay, now I hope some of you remembered that in the case of real four momenta, lambda and lambda tilde have to be complex conjugates of each other, because P has to be a Hermitian matrix. And so what am I talking about, having the lambdas do something special and lambda tilde does not, or vice versa? That doesn't make sense. And so, and indeed, it is a classical result that the Onshell three-particle amplitude in 4 dimensions, massless particles, is exactly 0 to all orders of perturbation theory. So what am I doing here talking about this stuff? And the answer is analyticity, right? If we remove the reality condition on space-time, or we allow for complex momenta, is another way of saying, then we can treat lambda and lambda tilde as independent variables, which is what we're doing here. And reality, going to real four momenta, corresponds to setting them equal to each other, or complex conjugates of each other. And so what we need to do is we need to say that all of the brackets vanish. That's also an easy exercise to see that for real momenta, lambdas and lambda tilde brackets have to be 0. So they're all degenerate. And if you take the limit where the angle brackets are 0 here, you get order epsilon to the minus sum of felicities, and this goes order epsilon to the positive sum of felicities. And we need that to, in the limit, we need it to vanish, not be a divergence. And that tells you that if the sum of the felicities is positive, only this expression can contribute, because this one goes to infinity in that limit, and vice versa. If the sum of felicities is 0, you can take either one, and it doesn't make it much of a difference. There's you can take a linear combination if you want, or they're the same expression, it doesn't matter. So you actually have 2 different cases. That's what these vertices mean. So blue means sum of felicities going into that vertex is negative, and white means the sum of felicities is positive. And in either case, you have a unique expression, which is fixed to all orders of perturbation theory. That is what is special about massless theories in 4 dimensions, is that the 3-particle S matrix, or rather its analytic continuation, is unique. Okay. So if we want to talk about this in a general quantum field theory, I have to tell you the states. So like, let's say we're talking about Yang-Mills or super Yang-Mills. We can talk about the plus coherent state or the minus coherent state, or just the plus gluon or the minus gluon. And I can talk about the minus, and I can draw pluses and minuses here to tell you the helicities. And when you put those H's into this expression, you get this. Oh, that's nice. That's the Park-Taylor gas. That's convenient. Still far from the general answer, but that's pretty convenient. And in any theory where you only have a single species of particle, or not a single species, but for each species label, there's a particle and its CP conjugate, like Yang-Mills, I don't really need to tell you that these are pluses and minuses. I just need, there's only one kind of particle, and it's the only thing that's different is the direction of time for that particle. So I can actually indicate the helicity flow with arrows. And that's kind of nice graph theoretically, because if you have a trivalent graph, and if it's a trivalent oriented graph that is free of pure sources and pure sinks, so anything that's free of pure sources and pure sinks, the vertices of the graph can be distinguished. There's either, if you have 2 in and 1 out, that's a blue vertex, and 1 in and 2 out, you have a white vertex. Okay, but if you, and so in fact, we don't even need to draw the helicities, we can just draw the arrows to distinguish them and talk about these amplitudes as being particular helicity arrangements of the 3 particles involved. Now, if you wanted to talk about massless QED, this diagrammatically is not enough because you have 2 kinds of particles. You have a spin 1/2 and you have a spin 1, and that means that you need to diagrammatically distinguish between, is this thing coming into this vertex a photon or an electron, and maybe you draw wavy lines for photons, but now everything starts looking way too much like Feynman diagrams, and I don't want to do it. But in general, you have to label the states of the particles. And there's exactly 1 exception to this rule, which is, well, 2 exceptions in 4 dimensions, which is for theories of maximal supersymmetry. So either n equals 8 supergravity or n equals 4 supergravity, there's a magic that happens, which is that the plus helicity state and the minus helicity state are in the same multiplet. They're related by supersymmetry. And that means that there's no need to distinguish between the plus helicity and the minus helicity. So in n equals 4 and in n equals 8, well, this expression is valid for n equals 4 not for n equals 8, but anyway, you have a unique three-particle vertex in either theory of these colors, and you do not need to talk about arrows. And for a substantial fraction of this talk, the only sense in which supersymmetry is playing a role in this story is that I have a smaller class of things to talk about. I can talk about graphs without arrows. That's really all the role of supersymmetry. If you put the arrows back on, there's a prefactor in front of all these functions. It's not a big difference. And the geometry is unchanged. Okay, so that is what is special about maximum supersymmetry in 4 dimensions. All right, but regardless of that and what the notation means, doesn't matter. The point is that once you have these little building blocks, these little 3-particle vertices in a 4-dimensional massless theory, you can start gluing them together in a way which is defined to all orders of perturbation theory and is a meaningful function of the external kinematics. Whether it's an amplitude or something, we're going to get to it. So I can take these things and start gluing them together. And here I will get a function which it happens to have n hat delta equals 0, so it's in this case it's rational function of the momenta. And it turns out that when you calculate it, it's the Park-Taylor amplitude. Cute. But that's not necessarily, a lot of these pictures don't mean amplitudes. And just to emphasize that, you can start adding more vertices and more edges, and this graph also makes sense. This graph makes sense, that graph. You can really start gluing these things together in any conceivable way, and every one of these pictures makes sense, whether or not it is an amplitude. Also, to hint, this one picture is the 4-particle 1-loop amplitude in a concrete sense. Whether or not these diagrams are directly encoding amplitudes is a totally unrelated question. My point right now is just that this is an interesting vocabulary of things for us to talk about, a thing that we want to understand better, because we know that it encodes the perturbative S matrix, and everything that we can write down in this way, we know from first principles is a function of the external kinematics without any redundancy. No ghosts, no gauge redundancies, no polarizations, nothing. So we can talk about this in QED, and this is also a tree-level amplitude in QED. But again, that looks too much like a Feynman diagram for my taste. So, and in n equals 4, we can just talk about gluing these 3-particle vertices together in some complicated way. And although it would be a hard exercise, I hope I've convinced you that this is a well-defined, the conversion of this little picture into a function, or an integral, or something with delta function, so some differential form, is unique. So if I draw this picture, I hope every one of you could, in principle, multiply the vertices together, every vertex together, integrate over the Onshell phase space of every single internal line, and you will get a unique expression that is a function of the kinematics, and it's well-defined. I will show you better ways of going from these pictures to rational functions in a moment. So it might take you a while to realize that what you got is this expression, but it is. That is the expression. And you can do this in any quantum field theory, massless in 4 dimensions. You can draw these pictures and compute and convert them in. And part of especially this afternoon's lecture is telling you how to do this a little bit more efficiently. Okay, so if your goal was to build up a vocabulary of these objects and better understand this class of functions, there's an interesting lever that you can start using to generate graphs from graphs. And that is adding a BCFW bridge. And in this case, the W is important, or actually I should be calling them BCF bridges because these are the things that predated the proof of the recursion relations with Witten. So there's a BCF paper and a BCFW paper. This is much more in the spirit of BCF. The idea is as follows. If I take any diagram or sum of diagrams, whether it's an amplitude or not, doesn't matter. I have some diagram like this, depends on these external kinematics, and I'm going to glue on what I call a bridge, which is a pair of vertices. Notice that this increases the number of internal edges by 3. I add this line, and this line, and thereby define a new Onshell function, or a new Onshell diagram that has the bridge attached to it. What does it do to the function? Well, notice that this thing adds 3 new internal lines, so 3 times 3-dimensional phase space integrals each, so there's 9 new integrals to do. And you have momentum conservation at these 2 vertices, so that means you have 2 times 4 delta functions. You have 8 delta functions and 9 new integrals to do. Now there's something unconstrained, and it's very easy to see what's unconstrained here. It's the scale of the momentum flowing through this vertex. Geometrically, right, remember the white vertex says all the lambdas have to be parallel. blue vertex tells you all the lambda tildes have to be parallel. And that means that lambda has to be basically lambda A up to a prefactor, and lambda tilde has to be lambda tilde B up to a prefactor. And now the momentum that's flowing into this sub-diagram, it's easy to see that it's shifted by I, by the momentum flowing through that edge. And indeed, this is exactly what you saw in Shruti and Yaroslav's lectures of the BCFW shift, the bridge. And so this new object depends on shifted momentum, A hat and B hat, which is defined in this way. And there's a pole here. This comes from direct calculation. And it's kind of easy to see that it's the right kind of thing to do. When you set alpha to 0, which means computing a residue here, you recover the left-hand side. So that's the undeformed thing. But as soon as you think about taking residues, I hope you think Cauchy's theorem. Because indeed, that is how we discover the recursion relations for trees. If you take, imagine now that this maybe isn't a single graph, but is a sum of graphs, doesn't really matter. We have an amplitude, which is a well-defined on-shell function, and I'm going to attach a bridge to it this way. That is not, the right-hand side is not something any of us intrinsically care about right now. I'm interested in the left-hand side, which I do not know. And what I get from adding this BCFW bridge is that this deformed business thing is the amplitude that depends on alpha. It's this thing, A hat. But I know that the left-hand side is just the residue at the origin, which deletes that edge. Okay? But we all learned in complex kindergarten that the residue in the complex plane is equal to minus the sum of the residues anywhere else. So that means that the amplitude we care about is this little residue in the complex plane. The pole at alpha equals 0. And using Cauchy's theorem, we can trade it for the sum of the residues away, including at infinity. And what we have is now a sum of residues where alpha is not equal to 0. Now we are in a very powerful position because the thing we want on the left-hand side, we don't know. But what are these poles away from the origin? Well, it's pretty easy to think. Just ignore this bridge for a second, and what you see is that these have to be poles, places in this amplitude where the amplitude blows up. And we know from Feynman diagrams, I wish I could do it without leaning on your Feynman diagram intuition, but we know that the poles of an amplitude or an amplitude integrand, a sum of Feynman diagrams, are when a propagator goes on shell. And if you draw a random Feynman graph and a random quantum field theory and you say, put a propagator on shell, all edges of an arbitrary graph can be divided into two categories. Those which break the diagram in two, these are called factorization channels, or those which when you cut the edge does not break the diagram in two. It lowers the number of loops. So those are called forward limits. So any sum of Feynman diagrams, if you look at all the poles of this sum of Feynman diagrams, gives you a factorization channel or what we call a forward limit. And of course, alpha is not equal to 0, and that means that the pictures we have are these pictures here. And these are the all-loop recursion relations for the loop integrands, or the sums of Feynman diagrams, which are robustly understood to be true in planar n equals 4, and almost certainly true in a much broader class of theories, with appropriate caveats. But for the rest of this talk, we're going to focus on this tree part. Okay. And it's this diagrammatic version of the recursion, which was discovered empirically by studying one-loop amplitudes in unitarity, that Brito, Gacazzo, and Fang made the discovery of the tree amplitudes. And then this Cauchy's theorem argument is due to Witten, where they wrote a paper together a few months later. That's why they're called the BCFW recursion relations. Okay. Now, one thing that's worth pointing out, here I've got all these diagrams now that don't have arrows in them, because I'm, simplifying my life by talking about supersymmetric theory, and maximally supersymmetric theory. But we can talk about, it's still meaningful to talk about the helicity components of a superamplitude or something. And that means that we can actually grade this according to how many minus helicities are coming into the amplitude. So there's a characteristic of any diagram you draw called M, which counts when you draw arrows on the graph, how many are incoming. Maybe we call it K. And M is just 2, so there's 2 in for every blue vertex and 1 in for every white vertex, and there's a pair for every internal edge, so M is just given by this, graph theoretically. And it's pretty clear that this recursion relation, so the amplitudes are also graded by M, and so there's a set of these graphs. You can apply this recursion relation for fixed M, okay? And for the forward limit, m has to be m plus 1. And for the factorizations, this graph here has to have the sum of these two m's has to be m plus 1. That'll be useful in a moment here. Okay. So when I told you before that one of the amazing properties of this recursion relation is that it solves this Park-Taylor, the first whimsical dream of that we had when we saw the Park-Taylor guess. Is there a formalism which, when you ask the question, what is this probability, it gives you one term and it's the right answer. And this is that formalism. BCFW immediately gives you Park-Taylor in one term whenever you ask the question, what is the scattering amplitude for m equals 2? And the reason is because of what we just had here. M left plus m right has to be m plus 1. And the m's go from 2 to n minus 2. And so that means that there's two terms in principle for the recursion. So let's look at this for 4 particles. By the way, the bridge part is just locked. And it's arbitrary, but it's locked. Every single term shares the bridges. So you have to pick out 2 legs. They don't need to be adjacent to each other. You just pick out 2 legs, and you put this bridge on everything. And that choice, we're going to come back to in a little bit. But the point is that the bottom part of these graphs has to be locked. And then you have to sum over all the junk that can appear left and right. Okay, so let's say we pick legs 1 and 4. So we have this bridge on the bottom. At the top, we need to have m left plus m right add up to 3, which means we can have and we have a m equals 2 3-particle vertex and an m equals 1 3-particle vertex. Well, there's only one way of doing that. It's the blue and the white vertex have to be both on the top. So you have this picture and you have this picture. However, and this is an interesting little caveat that sometimes you can remember, like you can wake up in the middle of the night and think, wait, what about those other diagrams? This is one of those kinds of things that we're going to throw away. Why? Because as an Onshell diagram, this imposes more than momentum conservation. You see, this vertex here says that all 3 of these Onshell momenta, their lambdas are parallel to each other. And then this white vertex says that all the lambdas here are parallel to each other, which in particular says that lambda 1 and lambda 2 are 0, or that angle bracket 1, 2 is 0, or that Mandelstam 1, 2 is 0. So in addition to momentum conservation, this actually imposes a factorization channel. And this diagram here, so it means that it is proportional to an additional delta function constraint, and so we throw it away when we talk about generic external kinematics. But maybe someday you're interested in looking at boundaries of amplitudes, and then maybe this thing might have to come up again. All right, but for the moment, let's just talk about generic momenta that don't satisfy additional delta function constraints, and that you have one term. So more generally, you can't have a white vertex on the left and a blue vertex or a blue vertex on the right. That's what gives you a single term. And now, but the legs I chose, or the way I colored the bridge, are both arbitrary choices. So if I had chosen instead of legs 1 and 4, well, instead of white-blue, I had chosen blue-white, I would have gotten this picture. And I want to make it very clear, this is not a sum over all diagrams kind of story. There's choices to be made when you apply these recursions, and you either get this diagram or you get that diagram, and consistency of this whole story tells you they have to both give you the tree amplitude. So you have this first little identity, which will come back to us in the afternoon. But when you look at, say, the 5-particle m equals 2, which is 2 to 3 amplitude, you get, again, you could have another diagram here where it was white on the left and m equals 2 on the right, but that one is proportional to 0 or imposes an extra constraint. So we only draw this diagram. And then we have to apply the recursion in that vertex. So we either glue this in or we glue that in. Either way, we're going to get a funny looking picture like that. Okay, this might look scary to you, but it's 1 term, not 25 terms from the Feynman expansion. And when you do 6 particles, the Park-Taylor application that led to their guess, you get 1 picture, recurse 1 picture, recurse 1 picture. And this is a scary looking picture to most students when you first see them. I mean, it looks like some 3-loopy object. And indeed, it's the residue of some particular 3-loop set of Feynman diagrams. But that's not the way I've defined them. I've defined them intrinsically as products of vertices. So even though it's a scary looking graph, I want to emphasize it's only one of them, not 220. And that continues for all multiplicity. So there's exactly 1 term. We've actually just directly proven the Park-Taylor, miracle. And maybe it's worth, okay, I think we started a few minutes late, so I've got a couple more minutes. Okay. Beyond m equals 2, you get more terms. There's more terms, but, and I want to give you a little bit of flavor for it. Say, for example, m equals 3, which would be the NMHV amplitude, I'm thinking about it as 3 to 3 scattering, with all of the particles being the same helicity, but again, crossing, if you want to apply it to colliders, use crossing. And on this case, we need the left plus the right to add up to m equals 4. So 3 plus 1 equals 4, good. But we could have also had 2 plus 2, or we could have had 2 plus 2 this way. So you just sum over all the ways you could have broken this up into pairs, and we threw away the one where this is flipped, where it's white on the left, and this vertex is over here, and we also threw away the one where this vertex was a 3-particle vertex, so where you flip these terms across the bridge. So we threw away some terms which are vanishing for generic kinematics, and we get these 3 terms. And then we start feeding in the recursions, and we get funny-looking pictures. Okay. And this indeed was the way, in fact, not exactly these pictures, because I preferred more like these pictures. But anyway, this is the way that the recursion relations were first discovered in terms of sets of diagrams that looked like this. And there are a few things that are very important to note that'll play a big role in this afternoon's lecture that I want to dwell upon right now. First, there is no BCFW formula. You get to pick whatever legs you want, not only at the beginning of this recursion, but when you look at the lower point amplitudes in the corners, you get to pick whatever legs you want there too. So there is absolutely no unique formula. And in this case, we have these 3 different functions, these 3 different weird-looking pictures. But what if I had chosen legs 1 and 2 instead of 6 and 1? I would have gotten these weird-looking pictures. And what is interesting is that in this case, this function, all 3 of these functions are different, and all 3 of those are different from these 3. So you have 6 different functions, and the answer is either 3 of them or the other 3 of them, and you have a 6-term identity that these 3 add up to the same as those 3. Okay? And in a more general case, if you go to higher m and higher n, what you have, you can vary the recursion of the vertices too, and that gives you many, many, many formulas which are all exactly correct. And they are extremely different. The pictures can look different. The functions that you get from the pictures, all of them look very different. So there's absolutely no unique formula. And this was a hint. I mean, this early on led some people to think that this was something analogous to triangulating a polygon, or a polytope. That maybe these formulas are like little individual, like little triangles or little simplices, and that the different versions of the formulas were just triangulating it in various ways. And that is one thing that the amplituhedron makes sharp. Another thing and this is probably the reason why these kinds of pictures almost never made it, or basically died as soon as they started appearing in the physics literature. So they disappeared from the physics literature. Unfortunately, at exactly the same time, they cropped the same exact pictures that started appearing in the math literature. Interesting side note. Is because it was recognized from day one, from the BCF paper, that these 3 functions, although they are different, are basically the same. What do I mean by that? I mean that even though these pictures look very funny and very different from each other, that this picture, if you just rotated the indices, was the same as this one, which is the same as this one with rotated indices. So that even though you have this like 3-term formula, it's actually can be written in a more compact way. You can just say it's this one plus rotate it by 2 plus rotate it by 2. And if you look at these pictures do not enjoy those symmetries. And the fact is that these pictures are redundant in their own special way, which is that there's millions of ways of drawing of different pictures for exactly the same function. And that makes it annoying as a physicist. So if you draw these pictures in a paper, which of the 10 different versions did you pick and why? And also, how do you even know that they're the same? All of this confusion is one reason why these pictures are annoying. And in the BCF paper, they just wrote a formula for the first one and they said plus cyclic. Okay? And that's the right answer. But how can we identify this? How do we get rid of this redundancy and characterize these functions in a way that allows you to see immediately that these things are actually all the exact same functions? And that's what we will pick up on when we come back. So I had a couple more slides, but I won't talk about them. So thank you very much.
Okay. Thank you. Any questions? for the break. Yeah.
So in the beginning, you said that from the geometry side, we have this a lot of symmetries, this infinite class of diffeomorphisms. So I was wondering if in the amplitude side, can we give meaning to the conserved charges associated to those physical symmetries that I have?
Yes, and but with complications and language. So in the case of n equals 4, we understand these symmetries just completely. That's the Yangian, and we understand the representations of the Yangian algebra pretty well. But talking specifically about the conserved charges is probably a little bit more involved, and also might depend on, well, in order to describe them concretely requires some presentation. So let's just say they're the conserved charges of the Yangian. For the non-planar ones, it's more confusing. So the diagrams have these symmetries, for sure, and you can generate them in an analogous way to the Yangian. So you can see some infinite tower of them. But you'll notice that very rarely is the amplitude a single diagram. Mm-hmm. And even when that's true, it's only like the tree. So at loop level, you have more diagrams. So, and the symmetries of this diagram might not be the same as that one. So when you look at a sum of diagrams like this, these three symmetries might not overlap. Mm-hmm. And I think that this is basically unexplored territory. Nobody has identified what these symmetries are, or seen that they intersect in a non-trivial way to be a symmetry of the full amplitude. But it's an interesting question because, in the case of the Yangian, n equals 4 had been a well-studied quantum field theory for 30 years, and it was before the Yangian was discovered. And it's funny because the n equals 4 was defined as the quantum field theory with the most conceivable symmetries. Mm-hmm. And then to find out later on that there's an infinite tower of more symmetries is kind of embarrassing. Mm-hmm. And it is worth knowing historically that the Yangian was discovered as a symmetry of these pictures, of these terms in BCFW, not from Lagrangians or anything else. So I think maybe there's some version of the Yangian waiting to be discovered for pure Yang mills. I don't know what that is, but nobody's really explored it yet. Okay. But it's tantalizing that every term has some infinite dimensional symmetries.
Thank you.
Yeah. Yes? Up back there? Sorry.
Yeah, okay. Yeah, all right. So I just needed a clarification. So for the loop amplitudes on the left side,
yeah.
Do you build the integrand this way, or is it the amplitude?
So it's the integrand. We're talking the argument I made for the locations of poles and whatnot. We're talking about the sum of Feynman diagrams. So I haven't done any loop integrals yet.
Is it the reason that you consider only tree amplitudes as building blocks? Because as far as I can see, you only argued the fact that you need gauge invariant building blocks, right? And then you chose only tree amplitudes.
Yeah.
Is it because you want the integrand? I mean, is that the only reason?
No, gauge invariant is more complicated here. It's not complicated here because the vertices are manifestly gauge invariant. There is a small distinction to be made. I'm not sure if this is related to your question, but the set of Onshell diagrams which are trivalent are meaningfully well-defined to all orders of perturbation theory. So these pictures here are meaningful because the three-particle vertices don't run, they don't have divergences, there's no loop integrand to talk about. So even though the pictures like what you get for the loop level recursions for 4 particles is you get one diagram surviving, and it's this weird one. And this diagram has n hat delta minus 4 equal to minus 4, so it's a 4 form that you have to integrate. And this is the loop integrand. But of course, the loop integral is divergent, so what are we talking about? And can we integrate it? These are kind of interesting challenges for this. But it is the sum of Feynman diagrams. But there's another question about gauge invariance, which is that this may or may not depend on your regulator. So for example, you can do this in DimReg. You can talk about Onshell functions in DimReg. You lose this 4-dimensional beauty that we have here. And then everything's gauge invariant. So that's nice. Any Onshell diagram is gauge invariant in DimReg. However, your answer might be regulator dependent. You can use another regulator, but then it might not be. There's some subtleties about pure Yang mills and about gauge invariance. It's tied up with regulator dependence in four or 4 minus 2 epsilon dimensions.
Thank you.
Yes, I was wondering about the generalization to masses, because of course we know that nature has also massive particles.
Oh, no, I don't think so. Not in the standard model.
Oh, then I'm happy to discuss this, but...
well, I mean, the standard model, the electron has m equals 0. And then the standard model is massless, except for the Higgs, maybe, which requires a mass. It has a negative mass, maybe, mass squared. But the entire, all the quarks and leptons are 0 mass in the standard model.
But after symmetry breaking, they...
You can describe them in terms of massless fields if you'd like, but they are not massless, or they're not massive. They have effective masses. So, yeah, no, you can unambiguously talk about the standard model in terms of massless fields with Yukawa couplings.
Okay. And can you describe this system also in your formalism then? So basically avoiding the use of internal masses, say in loop diagrams,
sure,
and every complication which arises with that?
Sure. So I mean that's a great question, and I'm sorry I was being coy before. I mean
I mean it's important to discuss.
So for the sake of these lectures, I'm going to take the massless limit. I'm talking about purely massless theories. But obviously in the standard model, masses arise through symmetry breaking, so they're kind of massless with a very specifically generated mass. Those kinds of theories might have very nice representations as some deformation of this story. Another way to see that would be to use something, there's a few different versions of what's called massive spinor helicity formalism, and there's probably Grassmannian connections to that story. But I don't think that's been fully worked out. So for me, at least, it's important that I have lambdas and lambda tildes to describe the particles and not any other degrees of freedom. But it could very well be, I mean, if somebody could write a paper tomorrow that the massive version is this version plus, it's like the same expressions plus the extra details in this massive formalism. But which version of massive spinor helicity you're using and what that story is going to look like remains to be seen. So for the sake of these lectures, I'm just going to assume m is 0 everywhere, and just rest assured that it's describing a lot of relevant theories.
So the problem is basically that for now we do not have a good formalism to describe this, and which allows us to generalize your ideas.
Yeah. So I mean, an example of where on-shell pictures and stuff like that make a lot of. You might think that you can compute g minus 2 in a massless theory. After all, it doesn't depend on the m. The m doesn't, come out. But it's a pain to define it in a massless. Like it is way, way cleaner to define the gyromagnetic ratio as the ratio of 2 3-particle amplitudes. So if you had a massive theory, these 3-particle amplitudes are not unique anymore. There are 2 different components and they can mix. And the gyromagnetic ratio is the ratio of these 2. And that's beautiful, easy to, I just explained it to you in a massive theory. That's what it is. That's the ratio of these 2 things, and you can compute it. And Nima and collaborators had a paper on massive spinor helicity where they included that calculation. And it's pretty elegant. I don't know if it's been pushed very far, and I'm not sure if it's the best way to do it. I think this is a great room for future work. I mean, somebody can find there's probably an elegant story to be told, but nobody knows it yet.
Okay, thank you very much.
Okay, thanks, Jake, again. So we have now a break. Just a small thing, I just noticed that the vending machine is not working. It ate my 70 crowns, didn't give me anything. So don't put any money in that vending machine, yeah? Hopefully it will be fixed. The coffee vending machine works, but not the food vending machine next to it.